When faced with a complicated problem, solve a simpler version first. You've probably heard this advice before. It's one of the most common problem-solving strategies in math. But let's be honest, what does simpler even mean? How do you know where to start or what part of the problem to break down? In the world of probability and game theory, there's a certain type of problem that can be easily tackled in this way. Today, I will show you this method, backward induction. Welcome to Luck by Numbers, where luck meets logic. Let's start with this popular brain teaser, 5 pirates. 5 pirates labeled A, B, C, D, and E, from the most senior to the least, are trying to divide 100 gold coins. Here's how it works. The most senior pirate makes a proposal to divide the gold. Then, everyone votes. If at least half of the pirates, including the proposer, agree, the gold is split. If not, the proposer is tossed into the ocean, and the next pirate in line gets their turn. The pirates vote based on 3 priorities. First, they want to survive. Second, they want as much gold as possible. And third, if it doesn't affect their survival or gold, they want to see others thrown overboard. Can you figure out how the most senior pirate can keep as much gold as possible while staying alive? The secret to solving this problem is to start backward. Consider the case when only 2 pirates, D and E, remain. D can propose anything and ensure it gets half the votes because he will always vote for his proposal. Therefore, D can propose giving 100 gold coins to himself and 0 to E. E certainly doesn't want this to happen. Now let's analyze the case when only 3 pirates remain, C, D, and E. For C's proposal to be accepted, he needs the support of at least one other pirate, either D or E. D will reject any proposal from C because he benefits more if the group shrinks to just 2 pirates. In that situation, D is guaranteed to get all 100 coins for himself. On the other hand, E doesn't want the group to shrink to 2 pirates, because in that case, he will receive nothing. Therefore, E will support C's proposal as long as it offers him something better than 0 coins. Based on this reasoning, C can secure E's support by offering him 1 coin, just enough to make E vote in favor of the proposal. Thus, C's proposal of 99 coins for himself, 1 coin for E, and 0 coins for D will be accepted. Following this logic, you will reach the stage where all 5 pirates are present. A proposes 98 coins for himself, 1 coin for C, 1 coin for E, and the proposal gets accepted. The problem looks daunting initially, but backward induction makes this so much easier. After you understand the basics of this problem-solving method, let's increase the difficulty. There are 100 lions and 1 lamb in the field. The lions are hungry, but they are not just any lions. They are perfectly logical predators. They'll only eat a lamb if it's in their best interest, and they know exactly how the other lions will react. If a lion eats a lamb, it turns into a lamb. So each lion must think carefully. Should I eat the lamb? Or will eating it make me the next meal? The question is, will the lamb survive? We consider the case when there is only 1 lion and 1 lamb. The lion will definitely eat the lamb, become a lamb afterward, and survive because there are no other lions to eat it. Now let's consider the case when there are 2 lions and 1 lamb. If a lion eats the lamb, it turns into a lamb and will be eaten by the remaining lion. So both lions would not eat the lamb, and the lamb stays alive. When there are 3 lions and 1 lamb, if a lion eats the lamb, the scenario reduces to the case of 2 lions and 1 lamb. As we've already seen, the lamb will not be eaten when there are 2 lions and 1 lamb. Therefore, with 3 lions, they know that eating the lamb won't put them in danger, since the remaining 2 lions will not eat the new lamb. This means the lions are happy to eat the lamb when there are 3 lions and 1 lamb. By induction, we find out that when the number of lions are even, the lamb will survive. and when the number of lions are odd, the lamp will be eaten. If these two problems seem too easy for you, let's level up and tackle this dice game. In the game of threes, the player starts by rolling 5 standard dice. In this game, the threes count as zeros, while the other faces count normally. The goal is to get as low a sum as possible. On each roll, at least one die must be kept, and any dice that are kept are added to the player's sum. For example, a game might go like this. On the first roll, the player rolls 2, 3, 3, 4, and 6. The player decides to keep the threes, which count as zeros, so their score remains 0. The other 3 dice are re-rolled, and the result is 1, 5, and 5. Here, the player keeps the 1, bringing their score to 1, and re-rolls the other 2 dice. The result of the re-roll is 1 and 2. The player decides to keep both dice, and their final score is 4. If a player plays optimally, what is the expected value of their score? Your first instinct might be to calculate the expected value of a dice roll, and you have 6 outcomes: 1, 2, 0, 4, 5, and 6. So you add them up and divide by 6. You get 3. You may be tempted to say, just keep all the dice less than 3 and re-roll those greater than 3. This is actually what I thought when I first came across this game, suggested by this viewer. However, if you analyze the game using backward induction, you quickly realize the game is much more complicated than that. Suppose we're rolling 1 die. The expected value is 3. We say E1 equals 3. Suppose we are rolling 2 dice. The rules require that we keep at least 1, so clearly we must keep the lower of the 2. The question is whether we keep the other one. Let the 2 dice be D1 and D2, and suppose D1 is less than or equal to D2. Case 1. We keep both dice. Our score is simply D1 plus D2. Case 2. We re-roll the second die. Our expected score is D1 plus the expected value of the reroll, which gives us D1 plus 3. We take the minimum of the 2 cases, so our expected score is D1 plus the minimum of D2 and 3. Finally, our expected score in this round is obtained by simply summing over all possible scenarios, and then dividing by 36 total scenarios. We get 79 over 18. Extending to the case of 3 dice, let's label them D1, D2, and D3, also in non-decreasing order. Case 1, we keep all 3 dice. Our score is D1 plus D2 plus D3. Case 2, we re-roll D3. Our expected score is D1 plus D2 plus 3. Case 3, we re-roll both D2 and D3. Our expected score is D1 plus E2. Notice that in case 3, we reduce the problem of 3 dice into the problem of 2 dice. This is backward induction at play. Taking the minimum of the 3 cases, our expected score is D1 plus the minimum of D2 plus D3, D2 plus 3, and E2. We get E3 equals 2261 over 2 times 6 cubed. Continuing this way, we get E4 and E5. E5 is the answer we need. The expected score is about 6.25 if we play optimally. But what's the optimal strategy? It is essentially encoded in our calculations above. To guarantee we get the lowest score possible, we must first memorize these 5 numbers. I'll use an example to illustrate our strategy. On the first roll, we get 2, 3, 3, 4, and 6. We put the 3s to the left, so the dice are in non-decreasing order. We keep the leftmost die by default. Next, let's decide whether we should keep the rest. We consider 5 cases. If we keep none, the expected value is E4, which approximately equals 5.83. If we keep 1, the expected value is 0 plus E3, giving us 5.23. If we keep 2, the expected value is 0 plus 2 plus E2, equaling 6.39. If we keep 3, the expected value is 0 plus 2 plus 4 plus E1, which is 9. Finally, if we keep all, the expected value is 0 plus 2 plus 4 plus 6, which equals 12. After calculating each decision's expected values, we keep only the first die, as it gives the lowest expected value. Suppose we reroll the remaining 3 dice, and get 1, 5, and 5. Again, we keep the leftmost die by default. For the remaining 2 dice, we calculate the expected values of keeping none, keeping 1 die, and keeping both dice. Keeping none gives us the lowest expected value, so we reroll both dice. Lastly, we get 1 and 2. We keep the 1 by default. For the last die, 2 is lower than the expected value of E1, which is 3. Therefore, we keep it. Finally, our total score is 4. As you can tell, backward induction is an extremely powerful tool in game theory and probability. Tons of similar problems require this strategy. I'll list a few in the pinned comments. If you want to become the best gambler using math, check out this video on the Kelly criterion.